Hello, my name is Ben Ashby. Welcome to the first pre-recorded lecture for Math 155. Today I'm going to be talking a little bit about the class itself before moving on to the first topic, which is coordinates. So Math 155 is the follow-on course for Math 154. In Math 154, you talked about one-dimensional problems. So for example, these can all be represented by points on a line. So for example, if you want to model how someone's height changes through time, you just need to know how that one variable height is changing through time. However, most problems in the real world exist in many dimensions. For example, if you want to model how someone's height and weight are changing, you need to have two variables that you're accounting for. Likewise, if you want to position something in space in 2 dimensions, then you need to have 2 pieces of information in order to locate it. And if you want to put it in 3-dimensional space, then you need 3 pieces of information. And of course, this could extend mathematically beyond more than 3 dimensions. We'll talk a little bit about this today. This figure shown on this first slide is actually information from 79 dimensions projected down onto 2 dimensions. So although we're very familiar with things just working in 3 dimensions, because that's the 3-dimensional space that we live in, mathematically they can be extended into many dimensions. And from a modeling perspective, those many dimensional problems are also really important because, say, if you want to model something like the COVID-19 pandemic, you need to be thinking about individuals who are maybe susceptible, who are exposed to infection, who are infectious, who may be hospitalized. Individuals may vary in terms of their risk or risk of infection or risk of severe disease. So all of these things require a many-dimensional approach. Okay, so in terms of the actual structure of these classes, I'll be releasing these pre-recorded lectures 1 to 2 days before the in-person teaching that corresponds to this material. And then when we have in-person teaching, we'll be going through problems. And the reason we do that is because it's much easier to learn mathematics by solving problems rather than sitting there passively and taking things in. So what I want you to do is go through these pre-recorded lectures, complete the notes. So there'll be PDFs on Canvas that are gappy, so there's room for you to annotate them. Fill those in, go through the material. There is sometimes material corresponding in the textbook as well. All the information about this is on the Canvas container. And then we'll go through problems in class. As far as the assignments and workshops and all things like that, all the information for that is on Canvas as well. Okay, so today we're going to be talking about coordinates. Hopefully this should just all be revision. There might be 1 or 2 things in here that are new to you, but you should be familiar, hopefully, about how coordinate systems work, and this will hopefully just be a recap. So we're going to be talking about coordinates, points in space. We're talking about the distance between points and also how we can project points in many dimensions down to a smaller number of dimensions, as is done in this figure up here. Okay, so a coordinate is any point, a 2-dimensional coordinate, that is any point in the plane that can be represented by an ordered pair x, y. And this ordering is really important because we're not just having a list of things. So for example, a list would be, say I have a cat and a dog. That's exactly the same as having a dog and a cat. The order of those 2 things don't matter, but the order of our coordinates matters. So in general, x and y is not equal, it's not the same as yx, unless x and y have to be the same thing. So generally, we wouldn't have xy being equal to yx in general. So if we want to plot a 2-dimensional point, we look at these ordered pairs and say, okay, suppose we've got point 0, 1. That means that we have 0 units in the x direction and 1 unit in the y direction. So we go along the x-axis 0 units, and then up the y-axis 1 unit, and that places us here. So that's the point 0, 1. If we have the point 1, 0, then we go along the x-axis 1 unit and up the y-axis 0 units. So that would place us here with this green dot. If we look at some of the other points, so for example, if we have -1, -3/2, -1, we go along the x-axis left 1 unit, and then we go down 1.5 units. So that would take us to roughly here. And of course, there's no reason as to why we need to work with either integers, as we've just seen here, we've got fraction, or even rational numbers, so we can have things like pi by 2. So this next point here, -2 pi by 2, well, that's going left 2 units along the x-axis and then up pi by 2. So pi by 2 is roughly 1.5, just over 1.5. So that's around here. And then if we just do one last example, 4, 2 is going to be in this quadrant here. We go along 4 to the right and then up 2 units here. So because we need 2 numbers, we say that this plane is 2-dimensional. If we needed 3 numbers, then it would be 3-dimensional. So if we have x and y values of the point P that are real numbers, so all of these examples up here, they were all real numbers, then we write this as the point P, so P is our point, is in, which is this little symbol here, and we say it's in R2. So what does that mean? Well, this is our point P. This symbol here just means in, or is an element of. And then this, on the right-hand side, this funny looking R with the 2 next to it, just says that there are 2 real numbers. So this extra line that goes through the R is just indicating that this is the real numbers. Sometimes you'll see this in a textbook as written just in boldface, but because we can't do bold when we're writing things out, we put this extra line through it to indicate what we mean. So if instead we have x and y are any positive real number, then we would write P as being an element of or in R2, because again, we've got 2 real numbers, but because they're positive, we can indicate this by a subscript plus. So that's saying that P is a point that has 2 positive real numbers. And then finally, if x and y are integers, then instead of the real numbers now, we write them as Z2. So this is saying here that we have 2 integers. That's what this Z2 corresponds to. There are other spaces as well, for example, the natural numbers, but you don't need to worry about these here really. Okay, so what we've learned in 2 dimensions can apply to 3 dimensions and 4 dimensions and so on as well, but it's harder to visualize what's going on in more than 3 dimensions, so we're just going to visualize what goes on in 3. So if we want to locate a point in 3-dimensional space, then we need to have 3 numbers. So to locate a point in space, we need 3 numbers are required. So we have now an x, y, and z axes, and we're going to say our point here is going to be equal to some values a, b, and c. Now here this c is going to, in this case, correspond to height. So how do we do that? Well, okay, now we go along the x-axis a units, along the y-axis b units, so that there is b units along, and then we go up the z-axis c units. So this gives us our point here in 3-dimensional space, ABC. Okay, so in 2 dimensions, we don't really have a choice in terms of orienting our axes, at least not in a way that makes any difference. But when we have 3 dimensions, we now have a choice as to what the orientation is with our coordinate system. So first of all, we say that a point P in R3 is an ordered triplet. So P is some point, let's call this X, Y, Z. So recall before in 2 dimensions, we had an ordered pair. Now we have an ordered triplet because there are 3 numbers. And we have a choice what we do with the X, the Z direction. So our Z axis could look something like this. So if you imagine the X and Y axis on this left-hand figure are flat on the table, and then this arrow for the Z axis, so our Z axis here, is making a right angle with that x-axis and is coming up from the table. So that's one option, and we would say in this case this is coming up. Alternatively, we could have oriented our z-axis as going down, so going through the table. These are obviously very difficult to draw in 2 dimensions, but if you imagine now, instead of coming up, that's going down or into, so down or into the page. So now we would have our right angle going down there. So why does this matter? Well, if we've got, say, a surface in 3 dimensions, you might want to know whether you're coming out of that surface or going into that surface. And so the orientation of your z-axis really matters. We're going to be using what's known as a right-handed coordinate system. And the way you can do this is by using your right hand and pointing your fingers along the x-axis and then curling them in the direction of the y-axis. So I'll do it this way around. You curl them in the direction of the y-axis, and then your thumb is pointing in the z direction. That's how you know that we're in this right-handed coordinate system. So if we apply it to this example here, if we put our fingers along the x-axis and then curl them around in the direction of the y-axis, then our thumb is pointing up. So go like this, the thumb is pointing up. If, however, in this case, our z-axis is pointing down on the right-hand side, then now our hand is upside down. So we put our fingers along the x-axis. Now when we curl them to the y-axis, our thumb is pointing down. So we'll curl them this way around. Okay, that's just about how we orientate ourselves when we have more than 2 dimensions in a Cartesian system. So I mentioned that we can have more than 3 dimensions. In general, mathematically, we can have any number of dimensions we want. And if we have Rn, then we say that points in Rn, where n is any positive integer. So this gives us an ordered n-tuple. So n-tuple is just the generalization of going from a pair to a triplet to 4 ordered things and so on. So we have an ordered n-tuple. And then we say that this space Rn is the real numbers that consists of all set of points defined by P in, so the symbol again, in Rn, if P is equal to a set of points, a set of elements, I should say, not points, x1, x2, x3, and so on, all the way up to xn. So in other words, there are n entries here. So this is how we write a point in Rn, where x1, x2, x3 are just like before we had x, y, z. Now we've got x1, x2, x3, and so on. So to give a few examples, if say we've already had a look at R2 and R3, if we had R4, that could be a point that's say -1, 2, 0, 4. That's got 4 elements. This is an ordered 4 tuple. This is a point in Rn. Of course, there's no reason as to why these need to be integer values. They could be any real number. So, for example, a point in R5 could be equal to pi e 0 -1/2 and 2. That's a point in R5. And although it's really difficult to visualize what's going on, obviously beyond 3 dimensions, these are really important when we're trying to solve different problems. So if we go back to this first slide here, where we had this, this antigenic cartography here, this dealt with what was going on in a 79-dimensional space. So here we would be in R79. And what was actually going on is that they looked at the interactions between different virus strains with 79 different antisera, so elements of the immune system, and see they looked at what the reactivity was of those 79 different antisera and then projected them down onto this 2-dimensional plane. So although this is just represented as a 2-dimensional plane, in reality, this is information that came from 79 dimensions. So although we can't visualize that with our limited human brains, we should be thinking about things in more than just 3 dimensions. There's nothing mathematically particularly special about 3 dimensions. Okay, so suppose we want to work out the distance between points in some n-dimensional space, in this case, in a 2-dimensional space. How do we do that? Well, we can just make a right-angled triangle in that space and apply the Pythagorean theorem. So for example, if we have a point given by x1, y1, and another point over here, x2, y2, we can join these 2 points up to make a right-angled triangle. And then we can work out the distance, d, as being the square root of x1 minus x2 squared plus y1 minus y2 squared. Why is that the case? Well, this distance along the bottom here is just going to be x1 minus x2, or rather it's going to be the positive value of it. So these lines here just mean take positive value, and here we're going to have y1 minus y2. So these are just going to be the lengths of the sides, and then to work out the length of the hypotenuse, we take the square root of the sum of the squares of the sides. So we can apply the same rule to more than 2 dimensions, in this case 3 dimensions, by again creating a right angle triangle. So suppose we've got a point P here equal to ABC. Well, we can see the distance from P to the origin. So here, 0, the origin is just 0, 0, 0, by making a right angle triangle. So if we make a right angle triangle, then first of all, we know that this, the height of this triangle is going to be C. So this length of this side is going to be C. What about the length of this diagonal line here? Well, if we call that, say, D1, well, D1 is just going to be a triangle itself in the plane. So we can make a right angle triangle here. And we know that it's going to be B units along in the y direction. And we know that it's going to be A units along in the x direction. So we know that D1 is going to equal the square root of A squared plus B squared. And then if we want to know D2, the length of this line up here, and D2 is just going to be equal to the square root of C squared plus D1 squared. So what we've done is we've made one little triangle in the XY plane, first of all, and then we've made a second triangle. So what's D1 squared? Well, D1 squared is just going to be A squared plus B squared. So D2 is just going to be A squared plus B squared plus C squared. So we can apply the Pythagorean theorem in 2 dimensions, we can apply in 3 dimensions, we can apply in n dimensions. And this gives us the distance between any 2 points. In this case, I've done it between the origin and a point somewhere in that 3-dimensional space, P, but we can do it between any 2 points in Rn. So for example, if we've got points P and Q in Rn, then the distance between them, given by this function here, so we call it d of PQ, so this function here, is going to be sometimes represented by these vertical lines here, and that just essentially means that the distance between P and Q. What we do is we look in along every axis, along every component of P and Q, and we take the difference between those 2 points, square them, so we've always got something that's non-negative, sum them up, and then take the square root. And this is what is going on in this side here. So to give an example, if we have a point P in R4, and let's call this 1, 0, minus 1, 4. And we've got some point Q is equal to 2, 3, a half, and 0, say. Then the distance between P and Q is just going to equal, well, we're going to take the square root, and I'm going to take the difference of each component, square it. So we're going to start off with 1 minus 2, and then square that, then add it to 0 minus 3, square that, add it to minus 1 minus a half, and square that, and add it to 4 minus 0, square that. So I'll leave you to do the sum if you want to, but that's essentially how we work out the distance between any 2 points. And this applies in any number of dimensions for Rn. Now, at the start, I talked about this antigenic map where we had these 79 different anti-sera that different strains of flu viruses were tested against, and that was projected down onto just 2 dimensions. So just to clarify what I'm talking about, this figure up here on the top right, we're going to talk a little bit more about this later this week. But in terms of what's actually going on here, we can't visualize on a piece of paper very well what's going on in 79 dimensions. The authors of this study found that the key information could really be described by what's going on in 2 dimensions. So that meant that they could essentially just drop all the 77 of the coordinates here and just project everything down on the plane. So we can do that again in general for any sort of space. And essentially what's going on here is if we've got a point, say ABC, so suppose this is a point ABC in 3 dimensions. So what that means is you go along A units in the X direction, B units in the Y direction, and then up C units in the Z direction. What the authors of this study and what you can do in general, what they did was to say, okay, well, say what's going on in the X direction isn't very important. We're going to drop the X direction and we project that now to a point just BC in the YZ plane. So we haven't completely got rid of that information in the sense of it still matters in terms of where it is in that 79 dimensional space as far as the antigenic map is concerned, but we can visualize it by projecting it down into a smaller number of dimensions. So here all we've done is we've just dropped what's going on in the X direction. That's why this axis is no longer represented. And you can think of this as being, say, suppose you want to project the shadow of something down onto a surface. So say you've got something like a ball or a pencil that exists in 3 dimensions. We could project what's going on in this 3-dimensional object down onto a surface by shining a light on it and looking at its shadow. So that shadow is a projection of what's going on in 3 dimensions. You could do a similar thing with coordinates. Okay, that's essentially it for today. Make sure you're familiar with terms like coordinates, points, the distance formula, and projection, and you should be able to answer these questions here. So first of all, what is the distance between this point -2, 1, 0 to the XZ plane? Just to make sure it's clear, the XZ plane is when you've got y equal to 0. So the XZ plane is saying, well, we've just got X and Z coordinates and there's no Y coordinate, Y is 0. And the second question is a little bit more challenging, but think about distances here. The triangle PQR has these different points. What you want to know is it an isosceles triangle? So remember what the definition of an